Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 11, Lesson 8 on the frequency and the period of trigonometric graphs. This is kind of our last major transformation of trigonometric graphs, and it will allow us to really unlock the power of these types of functions to model all sorts of different wave phenomena. So let's get into it right away. Horizontally stretching and compressing trig functions. And I want you to almost think about this. You've seen accordion players, if you're lucky, right? Or even like a slinky, right? That you can like stretch out and compress back, or any kind of spring. I want you to kind of think about that in terms of what we're going to be doing today. Now we can horizontally stretch and compress the sine and cosine functions. It's important to be able to do this, especially when modeling real world phenomena, because most periodic functions do not have a period of 2 pi, right? So normal cosine and sine graphs, just sine x and cosine x, they repeat their fundamental pattern every 2 pi radians because that's how long it takes you to get around the unit circle. The first exercise will review the general ideas between all horizontal stretching and compressing, which we saw back a few units ago when we looked at transformation of functions. Here we go. Exercise number 1. On the grid below is the graph of f of x equals 3 cosine x, and the function g of x is defined by the equation g of x equals f of 2x. Give an equation for g of x, that should be pretty easy, and explain how its graph would compare to that of f of x. All right, well, let's talk about the equation. That's simple enough, because literally all we need to do to have an equation for g of x is say that g of x is equal to 3 times the cosine of 2x. That's it. So where there was an x, there is now a 2x. Now, how would the graph compare to that of f of x? And remember, horizontal compressions and stretches kind of work counterintuitively to what you'd think that they would. Pause the video now and see if you can remember from our transformation unit, just in general, what would happen to the graph of f of x if we suddenly had the graph of f of 2x. We're going to horizontally compress it by a factor of 1/2. So we're going to horizontally compress by a factor of 1/2, right? So it feels like we should be stretching it out by a factor of 2. Oh, we multiply x by 2. But that actually takes the entire graph and it kind of accordions it in. Let's see how that's going to look. Let's take a look at letter B. Use A, graph g of x on the same grid. Verify on your calculator. All right, cool. So what we're going to do is we're going to take every point on this graph and we're going to sort of make it half the distance from the y-axis that it originally started. So let me go into red now. All right, now this particular point is 0 units away from the y-axis. So it is going to continue to be 0 units away from the y-axis. On the other hand, here, where we're at pi over 2, we now want that point to come over here to pi over 4, and this one at negative pi over 2 would be at negative pi over 4. This minimum value, which is at pi, now will be compressed, so it's now at a value of pi over 2. All right. This at 3 pi over 2, this is a little bit tricky, right? You can think about it as sort of 1 grid line, 2 grid line, 3 grid line. Will be here at 1.5 grid lines. And there at 2 pi, we're now going to be like that. So let's do it also on the other side. This thing will shift back here, here, and here. Now let's draw that in really quick. Whoops. And let's just stop it there and actually make it look a little bit more accurate. Well, I don't know if that's more accurate or not, but we'll keep it like that. Now, That is literally taking what I see in blue and squishing it in, compressing it by a factor of 1/2. But as we've talked about, obviously these graphs continue, right? They don't just stop there and there. So in fact, I would want to sort of continue to do this, have this down here, here, whoops, try that a little bit better, here, and back up to here. Likewise, this is going to come down to here, up to here, and up to here. Right? And notice what we're actually getting is we're getting far more waves in the same span that we started with. And let's take a look at this on the graphing calculator. I really want you to see this, and especially I'd like you to have it drawn better than the way it looks right now. All right, so let's put in our original graph really quick. So I'm in radian mode, which I want to be in. I want to do 3 times the cosine of x. All right, that's my first one. My second one is going to be 3 times the cosine of 2x. Now, that should be kind of good enough, but if we want to really see it using the same kind of grid that we have right now, I'm going to go into my menu, I'm going to go into my window settings, -2 pi to 2 pi by pi over 2 intervals. My y-axis goes from -5, come on, to 5 by 1s. That's a little bit better, and I'm also going to go into my settings and I'm going to turn my grid on, my lined grid on, so that I can really see it nicely. So by multiplying by 2, what I do is I take that sine graph and I go, I accordion it in, and I actually allow it to cycle faster. It's cycling twice as fast now, all right? We'll give it a name in a little bit, okay? But now my graph is going faster. Okay, so now let's continue and let's take a look at letter C. How many full cycles, full patterns, will g of x complete over a domain interval of 2 pi radians? All right, well, let's take a look. Okay, so let's just start at 0 and go to 2 pi, right? We're here. We get 1 full cycle, and we get 2 full cycles, right? So normally, we just get 1 full cycle, right? If that number that's multiplying x is 1, then we just get 1 cycle within 2 pi radians. But by multiplying it by 2, we speed our curve up, and we get 2 full cycles in. All right, let's take a look at letter D. The function h of x equals 3 times the cosine of 1/2 x. Use your calculator to graph this function. How many full cycles will it complete in 2 pi radians? All right, now, not surprisingly, right, by multiplying by 1/2, now instead of compressing our function, we're going to stretch it away from the x-axis by a factor of 2. Let's see how that looks on our graphing calculator. Here we go. So, menu, graph entry edit, function. Now we've got exactly the same thing, 3 times the cosine of, we could do 1/2 or 0.5, whatever you prefer, just don't forget the x. And look at that. Look at that black curve that's been kind of stretched away compared to the blue curve. And now, if I kind of look at it, right, I'm only getting 1/2 of a cycle, right? The thing is going down to its minimum, and then it's not even getting the rest of the cycle, right? It takes me actually 4 pi radians to get a full cycle in there. And let's get that graph kind of up on the graph grid now. In fact, let me go up here. And now what I'm seeing is I see something, let me go same color as what I have on my calculator, right? It now kind of looks something like this. Right, so it gets stretched away from the y-axis. It's almost like it's a slower curve, right? Now, right, it takes twice as much in terms of x to get in that full curve. And we only get 1/2 of a cycle within the 2 pi radians. All right, and this, I did it again. That is really impressive. If you were with me for my last video, I did exactly the same issue, which is kind of funny, given that I haven't done it in all of the videos I've ever done before, and now I've done it twice in a row. It's amazing. It's something about trig. All right, so let's talk about what's called the frequency and the period of a trigonometric graph. Let's take a look. The period and frequency of trigonometric graphs. The period, or wavelength, p, is defined as the minimum horizontal shift needed for a periodic function to repeat its fundamental pattern. The period for the basic sine and cosine graphs is 2 pi, and we've talked about that already. The period of the function depends on the coefficient b in the general equation y equals a times the sine of bx and y equals a times the cosine of bx. This coefficient is known as the frequency, and physicists would really like us to call it the angular frequency. All right, so let's take a look at what results we saw. Exercise number 2. Here we go. Consider the graphs from exercise number 1. For each below, state the frequency and the period. All right, now again, the frequency is simply the coefficient on the x, so that's a piece of cake, right? The frequency here is equal to, let me go back to blue. The frequency here is equal to 1. The frequency here is equal to 2, and the frequency here is equal to 1/2. All right, it's simply the coefficient on the x term. The period is how long it takes for the graph to complete a full cycle. Now, on a normal cosine and sine curve, when the frequency is 1, the period is 2 pi. All right, on the other hand, when we had our faster curve, right, its period, this is the red curve, was only a period of pi. Okay, it only took pi units before it completed its full cycle. And that kind of makes sense because we've speeded it up by a factor of 2. On the other hand, when we have 3 times cosine of 1/2 x, it takes a full 4 pi to go from this minimum back to the same minimum on the cosine graph, so its period is 4 pi. And you see this beautiful inverse relationship, right? As the frequency goes up, right, maybe from 1/2 to 1 to 2, the period goes down, 4 pi to 2 pi to pi, right? As the frequency goes up, the period goes down, and as the frequency goes down, the period, or wavelength, goes up. All right, so let's take a look at exercise number 3. Examine the results from exercise 2. What is true about the product of the period, p, and the frequency, b? Illustrate. Write an equation for this relationship in the box provided. So, right, we've got the frequency is 1 and the period is 2 pi. So 1 times 2 pi, well, that's equal to 2 pi. Here, we've got the frequency is 2 and the period is pi, so 2 times pi is 2 pi. Here, we've got a frequency of 1/2 and a period of 4 pi, and 1/2 times 4 pi is 2 pi. So it looks like the frequency, which is simply the coefficient on the x within the trigonometric function, and the period, which is the minimum horizontal distance it takes for the waveform to repeat itself, their product is always 2 pi. So the frequency times the period is always 2 pi. And therefore, if we know one, we can always calculate the other. In fact, you could even go on to say, if you wanted to, that the frequency will always be 2 pi divided by the period, and the period will always be 2 pi divided by the frequency. Now that's just another way of stating this particular equation. The period times the frequency, or the frequency times the period, will always be the constant 2 pi. And that way, as one of them goes up, the other one goes down, and vice versa. All right, let's take a look at exercise number 4. Determine the period of each of the following sinusoidal functions. Express your answers in exact form. And again, I want to really make sure you understand this terminology, because that's really important, right? The period is basically just if I have some kind of curve like this, and I measure this distance, that is the period. All right? The period you can really think of very nicely as the distance between two consecutive peaks or two consecutive lows, right? That's the period. P. The B is 4 pi over 3 and 2/3, right? So the B is simply whatever's multiplying the x. So in this case, right, we know that B is equal to 4. And we know that B times P is equal to 2 pi. So we know that 4 times the period is equal to 2 pi. I can divide both sides by 4. So the period, if I simplify that, will be pi over 2. In other words, right, if I were to graph this particular curve, it would repeat itself every pi over 2 units along the x-axis. Every pi over 2, it would cycle through another one of these complete waveforms. All right, well, what I'd like you to try to do is figure out what the period is for letter B and for letter C. And again, it only depends on the frequency, which is the number that's multiplying the x. Pause the video now and try to figure those out. All right, well, first, let me move this out of the way. All right, but keep in mind that graphical significance, right? Here, the B, the frequency, is equal to pi over 3. So pi over 3 times the period is going to be 2 pi. I think here it's going to be a little bit easier. Instead of trying to divide by pi over 3, let's multiply by 3 over pi. All right, those will all cancel. And in this case, the pi's will cancel, and we'll just be left with 2 times 3. So we'll end up with the period equal to 6. All right. In letter C, again, we've got our frequency is equal to 2/3. That means 2/3 times my period will be equal to 2 pi. Again, probably easier to multiply by 3/2 than dividing by 2/3. In this case, the 2's cancel, and my period would be 3 pi. So, you know, periods can involve pi's like they do in A and like they do in C, but they can also just be normal numbers like 6. Every 6 units along the x-axis, this curve would repeat itself. Every 3 pi units along the x-axis, this curve would repeat itself. And again, keep thinking, keep remembering what the period really means, because when we start to really get into applied problems, that's going to be huge. All right, let's keep working with it. Exercise number 5. For the function f of x equals 2 times the sine of 4x, do the following. Letter A. Determine the value of its period. Use this to help in labeling the x-axis on the grid provided. Fantastic. So what I'd like you to do is, just like we did in our last problem, figure out what the period of this is, and then we'll talk about how you can use that to label the x-axis to get a good graph here. Okay, well, our frequency, again, I want to keep using this terminology. Our frequency is equal to 4. So 4 times our period is going to be equal to 2 pi, which means our period is going to be 2 pi divided by 4, which is equal to pi over 2. Now, literally, that means that we will get an entire full cycle in pi over 2 units. So that's kind of what I want to make over here. I want to do pi over 2 over here, and I'm going to do negative pi over 2 over here. Now, trig functions come in quarters, okay? Let me kind of move all of this a little bit to the left so it's not getting in our way. Okay, trig functions come in quarters. So this is kind of good enough in a certain sense to just get a sense for what my scale should be. But if I actually want to know what I'm scaling my x-axis in, I might want to figure out what a quarter of pi over 2 is, and that's going to be a pi over 8. So literally, if I wanted to label the rest of my x-axis, if That would be pi over 8. This would be 2 pi over 8. This would be 3 pi over 8, right? And likewise, in the other direction, I'd have negative pi over 8, negative 2 pi over 8. By the way, 2 pi over 8 is the same as pi over 4, right? Which is half of pi over 2. Whew. Anyway, let's take a look at letter B. Graph the function without first using your calculator, then verify with the calculator. All right, well now I just want to graph the normal sine function, right? It's got a midline of 0 since we haven't vertically shifted it at all. It's got an amplitude of 2. So let's first say we've got our midline of y equals 0, which is just the x-axis. And we've got an amplitude of 2. Remember, the sine function starts at its midline. So the sine function is going to start right here. 1/4 of the period over, it's going to rise by 2 units above its midline. Then 1/4 of a period to the right, it's going to go back to its midline. Then 1/4 of a period, it's going to go to its minimum, and then back to its midline. We can then reverse that by doing this. And we should get something that looks like that. Again, I should slow down a little bit, make sure I actually get it through that point and that point, but let's take a look at it on the calculator now. All right, I'm going to bring my calculator open. All right, let's do this. I'm going to go in. I think I'm just going to open up a brand new document. Nope. Go into my graph. Okay, what do I have? I have 2 sine of 4 times x. All right, now, I really want to see that this, right, think about how quickly this thing is oscillating now, 4 times the rate of a normal sine curve. I want to make it look like this one. Now again, in theory, this one goes from negative pi over 2 to pi over 2. So I'm going to go into my menu, go into my window settings. I'm going to go negative pi divided by 2 to positive pi divided by 2. And I want it to go by pi divided by 8. Whoops, pi divided by 8. On my y-axis, not as important, but let's get that down. I'm going to go negative 5 to 5 by 1s. And there I have it, right? So I've gone from negative pi over 2, negative 1.571, to positive pi over 2, positive 1.571. And because I put my scale, my x scale in at pi over 8, it's now showing me, oh, I've got my peak 1/4 of a cycle past the midline. Then I'm back to my midline, then I'm to my low, then I'm back to my midline and reversing. Okay, cool. Let's see if I can go back into the correct one. I didn't. I'm scared, Joey. I'm scared to close it. Always hit full screen, not 4K presenter. All right, let's look at one last problem. Exercise number 6. The heights of the tides can be described using a sinusoidal model of the form y equals a times the cosine of bx plus c. If high tides are separated by 24 hours, which of the following gives the frequency b of the curve? Draw a rough sketch to illustrate and to help find the correct choice. All right, so let's talk about this a little bit, right? Tides are a wonderful example of a wave phenomenon, all right? So maybe, right, we're thinking to ourselves, you know, we're tracking the tides, right? The height of the tides, and this is x, but it's time, right? And we've got, let's say, high tide, and then it goes down to low tide, and then it goes back up to high tide, and back to low tide, and back up to high tide, etc. Okay? And they've told us that the high tides are separated by 24 hours. In other words, if I look at this, this will be 24 hours. Now, high tides are rarely separated actually by exactly 24 hours, but that's not the point, right? How can I use that to help me figure out what the value of b would be in this particular model? It's not asking for the value of a or the value of c. I don't want to know the midline or the amplitude. I just want to know the frequency. Pause the video now and see if you can think about that. All right, well in this case, what I have been told is the period. Literally, P, which is the period, is equal to 24. And technically, it's equal to 24 hours. It actually has units attached to it. Most periods do have units attached to them. Oftentimes, they are units of time. Hours, seconds, milliseconds. It's actually kind of cool. So what do I know? Well, I know that B times P is equal to 2 pi. So I know 24 times B is equal to 2 pi, which means that my frequency must be 2 pi divided by 24, and now I can cancel a common 2 in both of those, and in fact, my frequency is pi over 12. And that's it, right? So in one direction, we want to be able to take the frequency and figure out the period. That was our previous problem. In the other direction, we want to be able to take the period, and this is often the case when we're trying to create a model. We want to take the period, say, oh, this phenomenon repeats every 6 hours, or every 4 hours, or every 3 seconds, and we need to be able to come up with the frequency by honestly just taking 2 pi and dividing it by the period. All right, so let's wrap this up. Now, one of the cool things was, it feels like eons ago, we looked at the transformations of functions. We looked at vertically stretching and compressing functions. We looked at vertically shifting functions. We also looked at horizontally compressing and stretching functions. And now we've seen all of those with trigonometric graphs. Vertically stretching, that gave rise to the amplitude. Vertically shifting, that gave rise to the midline. And vertically stretching and compressing trigonometric functions gave rise to the frequency, which actually shows up in the equation as the number that multiplies x, and it gave rise to the period, which is the horizontal distance that it takes for a sine or cosine curve to repeat itself. Now, the one that you haven't seen yet is the horizontal shift, and we'll take a look at that in the next lesson. It's probably the least important of all of them, although some electrical engineers would probably disagree with me because that can get into like shifting electrical waves and what are called three-phase power. For now, though, we'll leave that to another time. I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.